So I wanted to go a little bit further with that transaction that we were investigating. It involved this Bitcoin address. So I guess I'm sort of just spying on this hapless person, um, and I don't have any particular ill will toward this Bitcoin user. I'm just kind of exploring what we can find out. Um, so here's a transaction ID that is related to the transaction that we were studying, um, and I did a little bit of work here with the command line. Let me get down to the right place. I'm sorry. Yeah. So here is where we get use Bitcoin client to get the raw transaction. I think you've done that before. And then here it is just as hex. This is I as I've been poking around, I've realized that this is the RPC version of the hex. On the actual blockchain, the byte order is reversed because everything is little Indian. Anyway, that doesn't matter for our purposes. So let's download sorry down decode this raw transaction into JSON format, and you get the transaction ID, which is also the hash. By the way, I found a way. I was curious, like, if how do you go from the raw transaction to this hash, and it's a double SHA-256 hash, and I might show you how to do it either in class or on a video soon. So this is the stuff that is encoded here. This 01 is that the version number, I guess, and then there's the size of this thing, and in bytes, this v size is related to SegWit. V size is sort of the effective number of bytes. I think it's the weight divided by 4, and because this is a legacy transaction, the weight divided by 4 is just the size in bytes. The lock time, we'll talk about that later when we talk about smart contracts. Um, what it's for is you can fix it so that a Bitcoin transaction, sorry, a U, yeah, is that right? A Bitcoin transaction output cannot be spent until a certain block height, but that feature isn't being used in this transaction. So you have a certain number of transaction ends. Here's the hash of the first one. Um, and okay, so how does this work? There's only one input here. Uh, let's just make sure that that's true. No, there are several inputs. So this is a slightly different transaction than the one we were looking at before. It's just related to the same guy. So here's the transaction ID. Um, this index is which output of the previous transaction that this UTXO um, was what the index was when it used to be an output instead of an input. This ASM, this is Bitcoin assembler, and this is hex. You'll notice that these are almost the exact same numbers, and this just is sort of, you can think of it as the machine code for the Bitcoin unlocking script. Notice there's a 47 here, but otherwise you've got 3044, et cetera, and here's 3044, et cetera, et cetera. And what this basically encodes is a signature followed by a public key. And it seems to me very likely that the first part is the signature, and probably the second part here is just a public key. Um, okay, so it's by presenting this public key that you prove that, right, so these two things together prove that this person owns the Bitcoin address associated with the payment for which it's kind of hard to, I don't, sorry, it's so awkward to explain all this stuff. This is how the person proves that they own the Bitcoin address corresponding to the UTXO, which this was before it became a transaction input. Ugh. So they have to present a signature of this very transaction that we're looking at, or certain parts of it, and then also present the public key corresponding to that signature, as well as the Bitcoin address. So the Bitcoin address can be derived from this public key. Sequence number, this is just all F's. It's not being used. And so this is another input. So for this transaction, there are two inputs. This is a reference back to the transaction that it came from. This is its index, 1. It's 0 based, so there was something else besides that. By the way, frequently these transactions have one input and two outputs, with one of the outputs being a change address. For de-anonymization, it's better to randomly choose which of the two outputs will be the change payment. So it might be that the 0th one for this particular case was the change transaction. And then again, there's the, look, the signature looks very similar, doesn't it? They both begin with 30. Yeah, I don't know why. Maybe that just says that a signature is about to occur. I don't know. All right, and now we get to the transaction outputs. Notice for the transaction inputs, the value is implicit. You have to go back to these transactions if you want to see what it is. But for the output, it's explicit. There are two outputs. Here's n equals 0, n equals 1. Are there even more? No, just 2. This tells you what the locking script is, and in class tomorrow I want to go over what this is and how it works and stuff. Right. So this is the assembler, or just the locking script expressed in the Bitcoin scripting language, and this is the hexadecimal equivalent. This one only requires one signature, and so the type of unlocking script here is pub key hash. So this seems like somebody's written a little program here, but actually everybody's using pretty much the same program, except for this. This is a public key hash, so that would be, that's variable. So this gets computed from the Bitcoin address, and maybe I'll say how in a second. And all right, so they go ahead and do that. Could we do that ourselves? I think we could. Okay, maybe we'll come back and do that in a second. And there's another output. So this one is the change address. This guy is just loaded. And right, this is that familiar Bitcoin address that we've been studying. So he's paying himself back 81 Bitcoins, and these other things are sort of similar. So let's come back here to our sort of snooping on this person. I decoded his address, and you might remember from last time that a Bitcoin address, where does it come from? It comes from the hash of a public key. And should we try to find a picture here? Sorry, it's Valentine's Day. Bitcoin address derivation. Let's just look at some images. Maybe you can find a good one. Oh, right here, this is the one we want. And so you've got a public key. It gets SHA'd, and then it gets RIPE-MD'd, and this gives you a hash, and then you get the base 58 check-in code, and then you get the Bitcoin address. So you can decode the address and do this backwards, and so you can separate out the public key hash and the checksum. So that's what we just did. So it turns out that the checksum is this, and the payload, quote unquote, is that. So what is that? That's the RIPE-MD hash of the SHA-256 hash of the public key. Okay, yeah. So you can also just base 58 decode this back into hex, and then you can see these things. So here's the version number, 00, followed by the hash, which stops at A4. And then the remaining 4 bytes are the check digit. Okay, so it might be kind of fun to go from the public key hash back to the address. So let's try to do that. Here I use bxhelp to show you what this does. So this is just RIPEMD composed with SHA-256. So if I apply this to the hash of the public key, it will take it back to now I'm confused. What am I doing here? Yeah, this is the hash, right? So I'm double hashing this, and then I'm base 58 encoding it. And that's giving me this. Is that the same as the original Bitcoin address? H6ZZ. Oh no, you know what it was? I saw this one H and then concluded that I had done what I was trying to do, but I was being stupid. This is just wrong thinking on my part. I thought that this would reproduce the Bitcoin address, but that's crazy because what needs to go here is the guy's public key, but I don't know what his public key is. I just know his public key hash. But one thing you could do is just base 58 check encode this actually. So maybe we should do that. So I'll copy that. And let's do bx base 58 check encode that, and that is the that's the sort of the target Bitcoin address, right? Let's go confirm H6ZZ. Yeah, that's our guy, H6ZZ. And I also sort of this bx function is kind of interesting. You know, associated with this Bitcoin address are potentially many UTXOs out there. And so what this command lets you do is find enough UTXOs corresponding to this address to pay off a certain number of Satoshis. So for instance, here's 1,000 Satoshis. So I say fetch enough UTXOs corresponding to this address to cover a payment of 1,000 Satoshis. And it just returned this. And did I look this thing up? I think I did, yeah. So this is a transaction for which where the UTXO occurs. It says the index is 1 and the value is this many Satoshis. All right, so now I looked it up and then I decoded the raw transaction, and let's look at the outputs. So there's index 0, but what we want is index 1, and it's paying to our target person, and here's the value. So this is where the value that he right, okay, so there's enough value here to cover a 1,000 Satoshi payment. That's all I asked for, so it might be that there are other UTXOs associated with this address somewhere else. Okay, yeah, all right, so let's stop there.